This video is on operating with radicals. We're going to be doing 4 more examples. So if I move this paper up, I'm on example 5. This says -5 to the 1/3 times -5 to the 1/3 times -5 to the 1/3. We want to simplify this. Now anytime you have something times itself, this can be rewritten as this one thing raised to the 3rd power because it's 3 times. Shortcut to multiplication is exponents. So this is actually -5 to the 1/3, but then all of that is done multiple times, so this is raised to the 3rd power. Because I have the -5 raised to the 1/3, but I have it done multiplied 3 times, so all of this is raised to the 3rd power. Now, to simplify this, whenever you have an exponent raised to an exponent, you multiply the exponents. So this becomes parentheses -5, because I want to keep that parentheses, raised to the 3 times 1/3 is just a 1. So then -5 raised to the 1st power is just -5. So even though this problem looked hard, looked difficult, it actually ended up being something very simple because of the structure of the problem. Always look for the structure and see how it's written, because a lot of times it will be much easier than what it looks like. On this next problem, we have the cube root of 64x to the 9th over 343. Now we first want to see if 64 over 343 is divisible. That's one thing we can do. So 64 divided by 343, hit math, enter, enter. It stays as 64 over 343. So that means it's not simple. That's not divisible. But then we look to see, can we take the cube root of 64? So the cube root, math, now I want to go down to the cubed root right here. I want to type in 64. Cube root of 64 is 4, so that's actually already a perfect cube. And what about 343? If I go back to math, cube root of 343 should be 7. So actually both of the radicands, both of the numbers in the radican are perfect cubes. So that will simplify automatically. Well, what about the letter? So we know that the cube root of 64, we have the cube root of x to the 9th, and we have the cube root of 343. This is what this actually turns into if we separate them, because we have 64 and x to the 9th on the numerator, number and then letter, and then we have the cube root of 343. The cube root of 64 we found out was just 4. No radical left over. The cube root of 343 was 7 with no radical left over. So what's the cube root of x to the 9th? Now the index is smaller than the exponent, so it should simplify. 3 goes into 9 3 times with nothing left over. So this is a perfect cube. This is x cubed 3 different times. So that means that we would have an x raised to the 3rd power, because 3 goes into 9 3 times with nothing left over. So our answer is just 4x cubed over 7. The coefficients cannot simplify. 4 over 7 is as far as that will go. And there's no other x in the problem, so nothing that we can do with the x cubed. And the x cubed does have a positive exponent, so that's our final answer. Even though this problem looks more difficult because of the numbers, it ended up being perfect cubes already. So all 3 of those were able to simplify perfectly. Moving on to this next problem, number 7. We have the 4th root of x to the 4th divided by 81. So these are not able to simplify inside of, together. So what we would want to do is to separate them. We have the 4th root of x to the 4th over the 4th root of 81. Now, again, we do not want a radical in the denominator, so before we rationalize, we want to see if we can simplify anything first. So the 4th root of x to the 4th, because the index and the exponent are the same, they actually cancel each other out. Just like a square root and a square, they are inverses of each other. So the 4th root of x to the 4th is just x over. Let's see if 81 is a perfect fourth. So if we go to math, and I want to go down to this number 5 right here because I want to change my index to be a 4. Now this is a newer calculator, so that means that this the way it's written is a little different than how it will look in an older calculator. So I'm going to show both ways. So I'm going to hit enter on this one. Now it says A&S, that was my last answer. I can actually go over to here and change it to be a 4. And then I want to type in the radicand of 81. See if it gives us a nice number. And it gives us 3. That means that the fourth root of 81 is just 3. So on here, instead of having the fourth root of 81, I can just put 3. So x over 3 stays as just x over 3. So this is our answer, x over 3. I do want to show in an older type of calculator what it would look like to do the fourth root of 81, in case you don't know how to do that. So I'm going to get an older type of calculator. Now this time, I'm still going to go to that math button, and I want to go down to number 5. Now last time, I could just type over the A&S on the newer calculator, so if I do that with a 4, I would still be able to do that, but it does not put it inside of where the x is, because this is saying that the 4 is that x right there. Because if I were to try and type the 4 now, because it's blinking on the x, it would just replace the entire radical. So I know I can't have that. I can type in the number 4 to say that's what I want my root to be, and then go to the math key down to number 5. And that does the same thing. So the fourth root of, and then 81, I still get the 3. On this last problem, this one looks more complicated, but as you can see, we have 12 divided by 4. We don't even have a radical right now. But do you notice that these are rational exponents? These are fractions, which means we can turn them into a radical. But we don't want to do that yet. We want to see if we can simplify anything first. So right now we have 12 over 4. That gives us a 3. 12 over 4 is 3 in our numerator. We do have a y and a y, so since we have two y's, we actually want to subtract them because we're dividing. Now, 1/3, so we take our numerator of 1/3, our y to the 1/3, so we take our exponent of 1/3, 1 divided by 3 in parentheses, minus, parentheses, 1/2, close parentheses. And that gives us a negative decimal. So I want this as a fraction because fractions are easier to work with. So we have a negative 1/6. So this would be y to the negative 1/6. Now the problem with this is that we're not allowed to have negative exponents, so we do need to fix that. This would become, so that negative 1/6 is only attached to the y, so only the y is going to move. So we keep the 3 in the numerator, then we have y to the positive 1/6. Now, a fraction exponent turns into a radical. So this actually turns into 3 over. We will have a radical. Our radicand is the base, so that's our y. Our index is the denominator of the fraction, so it's going to be the 6th root. And our 1, our numerator, is the exponent of our y. We cannot simplify the 6th root of y any further, and we're not allowed to have a radical in the denominator. So again, this goes back to rationalizing the denominator. Rationalize the denominator. I'm going to rewrite this problem of 3 divided by the 6th root of y. And now we need to rationalize the denominator. We want to get rid of the 6th root of y. So when we got rid of the square root of something, we squared it. To get rid of the sixth root, we raise it to the sixth power. But I can't just raise it to the sixth power because it's not keeping it the same value. So how do we do this? Before, we just multiplied it by the denominator, the radical in the denominator. So if I multiply it by the sixth root of y here, I only have the sixth root of y squared. I need sixth root of y to the sixth power. So this isn't enough. I do know that I still have to keep it as a value of 1. So this is still just times 1. This value is 1. But like I said, I need the sixth root of y to the sixth power on the denominator. I only have y to the second power because it's y times y. So I need another one. So if I do the sixth root of y, so I have a value of 1, but now I have the sixth root of y to the 1, 2, 3, to the third power. I need another one. Sixth root of y, sixth root of y. So I now have sixth root of y, 1, 2, 3, fourth power. Do it again. The sixth root of y in the denominator, sixth root of y in the numerator. So we have 1, 2, 3, 4, 5. This is sixth root of y to the fifth. Almost there. Do it again. Sixth root of y, and then the sixth root of y. So again, we still have 1, 1, 1, 1, 1. Now, sixth root of 1, 2, 3, 4, 5, 6. This will become y to the 6. This sixth root of y to the 6 will finally cancel each other out. So now we will have, on the denominator, the sixth root of y to the sixth power will just be y. The numerator, our original coefficient was 3. There's a 1, 1, 1, 1, and 1. So it's just 3 times 1, 5 times, so that's still just 3. Then we have the sixth root, so this is index, 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 index are all the same. So we'll have the sixth root of, we have y to the 1, 2, 3, 4, 5 in our numerator. Y to the fifth power in our numerator. So let's see if any of this will simplify. 6 is our index. It is bigger than our exponent. That means that we will not be able to simplify this further. The y's cannot do anything because this is a radicand. This is a coefficient. Then the coefficients 3 and y will not simplify. So that means our final answer is 3 times the sixth root of y to the fifth, and all of that over just y. This one is a more complicated one because of the root of our radical, our index being 6. That means that we need to the sixth power. So we needed it 5 more times because we already had 1. So if we needed it to the 9th power, we would have needed 8 more of them. Same on the top. So this one was a more challenging problem.